Today we're going into the last topic. And that is friction. And we're going to do sort of three different types of friction. The first one is square threaded screws. The second one is belt friction. And the third one, I'm breaking up into two pieces. So this third one is bearings. And we're going to do two types of bearings. Journal bearings. You can think of that as the kind of bearing that a spindle or an axle goes through. And the second type is thrust bearings. And none of these are going to take super long. We might be done with all of these possibly by the end of Tuesday. And then that's the end of material in this class. So before I go into the first one of these square threaded screws, all of these, this is something to keep in mind for applying these techniques. These relate to drive friction only. Not viscous friction. So you have to be careful of using these calculation approaches for joints that are surrounded by oil or something. It works perfectly for dry lubrication, like waxes and small amounts of liquid and graphite, graphite powder, that kind of stuff. It works perfectly for that. Okay, so the first one is square threaded screws. And what we're talking about here is screws like this. Let me try to draw it. So here are a couple of threads on the screw. And they articulate with oops. Oh. So there are threads on the thing that it's attached to. Okay, so that's a square threaded screw. It's not this. Um, let's, that's like a, that's a very irregular screw. Usually the threads are at sort of regular intervals. Um, am I going to redraw it though? But anyways, this, notice the difference in the shapes of those threads. The one on the right comes to a point. Um, the one on the left, it doesn't come to a point. Um, these are, okay, so we're dealing with the type on the left. Um, the benefits of this are that it can support much bigger loads. And it also has the benefit that the forces applied by the surrounding threads to the threads of the screw uh, don't um, don't do damage to the threads because of the direction that they're. Actually, let me say it better. The threads don't produce forces that explode the surrounding threads. Um, and the way that happens in a standard screw is if you think of the contact force between the threads of that standard screw and its surroundings, um, look at the direction of like a normal force. In this case, pushing out into the screw like this. That means that this thread is pushing out on the surroundings, and that's applying an outward force on the surrounding threads that's pushing the surrounding threads away. Okay, and you can get damage like that if the forces are big. It's also easier to just wreck these threads because the closer you get to the point, the skinnier the amount of metal is that has to resist those forces. Yeah, right. Um, so why would you ever use these standard ones? They're just cheaper and easier to make. Um, well, for wood, yeah, for wood. Um, cheaper to make, faster to make. Maybe those are the same thing. But if you want to do something that uh, where big loads are going to be supporting, you need to use square threads. Okay. So the calculations for square threaded screws are going to be based on something you did in Calc 1 and may have wondered why. And now we have an application for it. So the calculations for square threaded screws um, are based on blocks sliding on inclines. So let's do an example and remember how this works. Um, so let's say you have an incline like this that makes an angle of 20 degrees with the horizontal. Let's say that this box has a mass of 100 kilograms. And let's do two calculations. We'll say that the coefficient of static friction is equal to 0.2. And let's think of a force going this way. I'll call this the force up, FU. Don't say it like that, though. And then let's think of a force going this way, FD. And we want to calculate two things. What's the required FU to get this to slide up the ramp? And then what's the required FD to get it to start to slide down the ramp? In order to do both of these, we're going to use a sort of unusually rotated coordinate system. The one that we always use for these has the y-axis pointing straight out of the surface, and then the x-axis is parallel to the surface. And notice that these forces FU and FD, I'm setting them up to be horizontal. Okay, that makes the calculations a little bit more of a nuisance, but I'm going to do it anyways. Okay, so for part A, let's draw a free body diagram. We have a weight force of the mass times 9.81, so 981 newtons. And we're trying to get it to slide up the ramp, so I'm only going to deal with this force on this one, and that's not the right direction, it's horizontal. So that's FU. And then there's a normal force and a friction force. And if we're trying to get this to slide up the ramp, which way is the friction force going to act, the static friction? Yep, so it's going to go down the ramp. This is the normal force. And if we're trying to find the exact value at the boundary where it's just about to start moving, we're going to assume there's no acceleration, but the friction force is as big as it can be. And that means that the magnitude of this friction force is 0.2 N. Okay. In our rotated coordinate system, calculating the friction force and the normal force is easy, but calculating FU and the weight force is kind of a pain because they're not aligned with the axes. But I'm going to show you a nice way to do it. So if you think of in our usual coordinate system, before you rotate it, the weight force, mg, is 0, negative 981. And that force vector force up is equal to the scalar Fu for the x component and 0 for the y component. And now if we want to go from this coordinate system to this one, what's the rotation we have to make? The magnitude is 20, because that's the magnitude, that's the angle between the horizontal and the incline. But is it clockwise or counterclockwise? Counterclockwise, so is theta going to be positive or negative 20 degrees? Positive. Counterclockwise is positive. And so our rotation matrix is cosine of positive 20, positive 20. Sine of positive 20, negative sine of positive 20, cosine of positive 20. And we're going to multiply that by, the new weight force. The weight force in the new coordinate system then is going to be equal to Q times 0, negative 981. And so we're going to multiply, this matrix is 0.940, 0.342, negative 0.342, 0.940, and we're going to multiply it by 0, negative 981. And so you get an x component of negative, well, I'll keep the negative where it was. So an x component of 0.342, actually, this is the last time I'm going to erase it. 0 times 0.940, that's 0, plus 0.342 times negative 981, that's the x component, and the y component is negative 0.342 times 0 plus positive 0.940 times negative 981. And can someone please calculate those for me? Oh, do I have it? Yes. Woo! So the weight force in the new coordinate system is negative 335, negative 921.8. Well, that looks longer the way I did it, but if you just have it programmed in your calculator, it's like this. Tick, 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 done. You don't have to think about trigonometry or anything like that. You just have to think about how the coordinate system is changing. And then we have to do the same thing for the force up in the new coordinate system. Bless you. That's equal to 0.940 times 0.342. 0.342, negative 0.342, positive 0.940, multiplied by the force up the ramp in our original coordinate system, which is Fu0. And that comes out to be 0.940 times Fu plus 0.342 times 0. And then negative 0.342 times FU plus 0.940 times 0. And you come up with a force up the ramp in the new coordinate system of 0.940 FU. Nope. And then for the y component, negative 0.342 FU. Or if you don't want to do it that way, just set up the right triangle trigonometry and do it the way you did it in Physics 1. They both give you the same answer. Okay, so Newton's second law. The forces we have are the two that we just calculated, the normal force and the friction force. So the weight force is negative 335, negative 921.8, plus the applied force up the ramp, 0.940 FU, negative 0.342 FU, plus 0N, plus negative 0.2 N0, that's the normal force and the friction force. And those are equal to the mass times acceleration. Well, this is statics, so it doesn't take much guessing to know that the acceleration is going to be 0. But we're looking, the reasoning is we're looking for the point just before when that friction force is maximum and the acceleration is still 0. The thing hasn't started moving yet, but it's about to if you increase that force a tiny bit. And so we have a system of two equations for two variables. And so I'll write this as 0.940 FU minus 0.2 N is equal to 335. And then the second equation says negative 0.342 FU plus N is equal to positive 921.8. And you can solve that with reduced row echelon form, or you can use substitution. This one, the second one says N is equal to 0.342 FU plus 921.8. Substitute that into this one. And it gives you 0.940 FU minus 0.2 times the quantity, 0.342 FU plus 921.8. Is equal to 335. Can someone just go through that algebra and tell me what you get for FU? $595.8. Okay. Okay, so if you want to get this thing moving up the ramp, that's the horizontal force you have to apply to the right to get it to move. Now, based on that, can you make any statements about what we're going to see for the force FD to get it moving down the ramp? So that's one thought, and it's probably going to be sort of in the same ballpark. But if you think about the way gravity is acting here, there's going to be some effect that when you're trying to move it up the ramp, gravity is fighting a little bit. And when you're moving down the ramp, gravity is helping a little bit. And so you're always going to get a bigger magnitude of force trying to push it up the ramp than you're going to get to push it to get it moving down the ramp. And that's going to be something that comes up in these square-threaded screw problems. So now we're going to calculate FD required to get it moving down the ramp. It will be smaller than FU, because gravity fights motion up and helps motion down. Okay. So let's draw a free body diagram again. So this is part B. Now we don't have the force pushing up. We only have the force pushing horizontally to make it go down the ramp. That's FD. And we have the same weight force of 981. And we have the same normal force, N. But now that force FD is trying to make it move down the ramp, and friction is resisting that. And so the friction force is 0.2 N. I hope I made the coefficient big enough for it. It's possible that if you make that friction force too small, it won't take any force FD to make it slide down. It'll just slide down under its own weight. I hope I made it big enough. Okay, well, the weight force is going to be the same. We don't have to calculate the components in the new coordinate system again. The force FD is going to look just like this one, except opposite. So it's going to be negative 0.940 FD, positive 0.342 FD, sorry. So Newton's second law says negative 335, negative 921.8 plus 0N plus positive 0.2N 0 plus negative 0.940 FD, positive 0.342 FD is equal to zeros. And so we get two equations. 0.2N minus 0.940 FD is equal to 335. And positive N plus 0.342 FD is equal to 921.8. So N is equal to negative 0.342 FD plus 921.8. And then substitute that into the first equation. And you get that 0.2 times the quantity, negative 0.342 FD plus 921.8 minus 0.940 FD is equal to 335. And can someone do the algebra of that and calculate FD for me? I hope not, but if it is negative, well, it might be negative. If it is negative, that means that I didn't make my friction coefficient high enough for this to stay up on its own. Damn it. Negative 149.30. Okay. Well, I am not doing this over again. Okay, so what does the negative mean? That means to keep this at rest, you actually need to pull up the hill. Because I made mu sum s sub s too small. Cry face. That's actually sort of an alarming picture. But anyways, that's the idea. That's how you do the calculation. And if I would have made my coefficient of friction 0.4 or something, then we would have seen a number here that was smaller than the number required to. So in this case, it became so much easier to push it down the hill that to keep it at rest, you actually have to hold it up the hill. Okay. You understand what I'm talking about, or do we need to do that again? Okay. So anyways, the moral is it's harder to get the block moving up the ramp than down the ramp. Okay, so how does this relate to square threaded screws? Let's look back at the picture of a square threaded screw, okay? And think about what we have here. You can think of the articulating thread, the outside thread, okay, as being a surface that the screws thread slides along, right? Um, as you're turning this, it's sliding up what you can think of as like a curved ramp, okay? Like instead of thinking of the incline as being straight, think about like pushing a block up a spiral upward, up a helical path. And then remember that the calculation of friction force doesn't take into account surface area in any way. It seems that's one of the oddest seeming things about the friction calculation. There's nothing in it saying, I mean, all it does is you take the coefficient of friction and multiply it by the normal force. You don't then multiply that by the surface area of contact between the ground and the, okay, so that's weird, but that's just how it is. That's how the calculation works. Which means, in other words, that we can think of this not as a long, curved helical path sliding along another helical path. We can think of it as just a single block, let's say this point here, being slid along that helical path. So now we're going to replace this idea of, I must have that drawn somewhere. Okay, so now we're going to the square threaded screws. So we're going to think of this screw as this, okay? You don't ever want to really build a screw that way. That little piece of metal attaching will slide and this thing will tilt in there. But this is mathematically how we're going to think about it. The entire thread of that screw is just condensed into that one little block, okay? And that one little block is sliding along a helical path like this. You follow what I'm talking about? Okay, so the red is the outside thread. This little box is the screw thread. And we can do that because the surface area of contact, the area of contact doesn't matter. And if you imagine looking at that over from the side, that's you with your stupid face. Sorry, that was not nice. You know who that looks like? The Count from Sesame Street. Yeah, it does. Hey, it does look like a bird. But this is supposed to be the mouth. Like that. That little block sliding up that ramp. Anyways, so that's, if you look from this perspective, what you see is this is the thread, the outside thread. And this is the thread of the screw. And you have some angle here. You have a force pushing straight down here. That's like if you're, if you're using a square threaded screw to jack up a car, say, that's the weight of the car. So I'm going to call this W. In our last example, it was the weight of the block itself, but in this case, it's not the weight of the screw. It's not the weight of the screw itself. It's the weight of whatever that screw is supporting, because you're using this to support big loads. And then you have a horizontal force. No, I already have a W. Call this Q. Okay. And what we're going to figure out is that the force Q required to make this block slide up the ramp. What we're really calculating is the force Q required to make that screw start to turn up the outside thread. And then after we're done with that calculation, we'll think a little bit about what the Q is, how that relates to physical things. Well, let me just say it once here, and then I'll get it in your notes later. But, so what's the equivalent of this force Q that's pushing there? Well, if you're, it depends on what the mechanism is for turning this screw. But with a, yeah, it could be a screwdriver or it could be a big lever arm to turn it. What it never would be is actually applying a horizontal force to the back of the thread. That's what we're calculating though. Okay, so that's not really a physical force. That's something we're going to end up replacing later. But it just makes this analogy work really nicely. So we'll deal with that once we get to the end. Okay, so let's say that we have a screw. So we have a square threaded screw supporting a force. This is the force W we're talking about, of 2,000 newtons. And the thread is at an angle of 5 degrees. And we want to calculate two things. What's the force Q required to start to lift the load? And then second, we'll figure out what force going the other direction. What's the force Q required to start to lower the load? Okay, so for part A, a free body diagram of the block, which is the thread of the screw. I'm going to exaggerate this angle because 5 degrees makes it sort of hard to see what's parallel to what. Okay, so we have a downward force that isn't the weight of this block anymore. We're dealing with forces that are a lot bigger than the weight of the thread on a screw, so you don't even really have to take that into account. And what did I say, 2,000 newtons? So there's a downward force of 2,000 newtons. And then we're talking about raising this load, so the horizontal force is going to be this way. That's our Q. And then we have a normal force and a friction force that's resisting moving up the ramp. Oh, did I give a coefficient? Okay, let's say the coefficient of friction these are going to be pretty low because these are going to be oiled surfaces. Let's say that's 0.1. I think that should be okay because this angle is so small. So 0.1 times the normal force going down the ramp. And now Newton's second law says we have 0n plus negative 0.1n 0 plus what's the cosine of 5 degrees? Okay, so this Q force is going to be 0.996 Q, and then negative, what's the sine of 5 degrees? 0.0872 Q. And the normal force is going to be, not the normal force, sorry, the 2,000 Newton force is going to be negative 0.0872 times 2,000, and then negative 0.996 times 2,000. And again, those are equal to 0. Can someone just multiply these out for this vector? What's 1, 2, 3? That's 174.4. Okay. $19.92. Okay, so this gives us a system of 2 equations. The first one says negative 0.1 times the normal plus 0.996 Q is equal to positive 174.3. And the second one says N minus 0.0872 Q is equal to 1992. Can someone solve that system for me? And we're trying to find the value of Q. We don't really care about that normal force. 2084? Okay. Okay, that was a little higher than I expected. So, okay, 378.3 newtons. Okay, so okay, that's great. So we did what we were looking for. After I'm done with this example, one of the last things we have to do is figure out how to express that as a couple. What's the couple you need to apply to this screw? Because that's the force you would have if there was like a little notch in the thread somewhere and you were pushing on that notch in the thread with a stick. That's the force you would have to apply. But if you have a bigger moment arm than that, then the force is going to be a lot smaller than that. And so that's not a realistic way to turn a screw, but that's our answer for part A. And now for part B. So what do we expect this force to be to get it going down the ramp? Bigger or smaller than 378? Smaller, and hopefully not negative. Otherwise, basically, if we got a negative answer, that would be like, think of like a jack for a car, where if you jacked it all the way up and just left it alone, it would drift. It wouldn't hold the car up unless you're applying a force. Okay, well, let's do it. So free body diagram in this case. We have a downward force of 2,000. This time the horizontal force is to the left, and I'll call that Q again. And then we have the normal force, and resisting the motion down the ramp is the friction force, and that is 0.1? Yeah, 0.1 N. And so Newton's second law says 0N plus positive 0.1 N, 0, plus negative 0.996 Q, positive 0.08, what was it? 0.0872 Q, plus negative 0.0, well, this is going to have the same magnitudes as these, so negative 174.3 negative 1992. So that's all the forces, and that's equal to zeros. And so we get two equations, 0.1 times the normal minus 0.996 Q is equal to 174.3. And the second equation says N plus 0.0872 Q is equal to positive 1992. And can someone calculate Q and tell me what that is? Negative again? Yay! I'm gonna use the positive one. Okay, 24 point what? Okay. So in either case, you had to apply a load to make the thing move, but to move with the help of gravity, it's less of force you have to apply than to fight gravity to move up. Okay? And this is how I want to see you be able to do the problem in this way. I don't want you to just use a formula, which I want you to notice too. I mean, I could have just derived it, or you could go home and follow these steps and derive it for a general W and Q. Do it once up the ramp, once down the ramp, and you just come up with a sort of ugly, but a formula where you could just plug in values. But I want you to sort of make sense out of how this fits together, because otherwise I don't really think there's much point in studying this in the first place. Okay, yes, because for the second one, I didn't treat my Q as a default this way. You're thinking, yeah, that totally, if this was how I defined Q for both of them, then we should get a negative value of Q. But for the second one, if you look at my 3-by diagram, I see any other questions? Okay, there's two more things we have to address, but they're simple. The first one is we don't really want that value Q. We really want a couple that you have to apply. I'll call it M. Well, but if you're thinking of the screw like this, then this distance is just the screw's radius. I'll call it little r. Okay. And so the couple you're applying is just equal to U times R. And then that's a couple that you can apply however you want. You can put a big handle on it, and that's the couple you'd have to apply with the big handle, or you can, put a foot pusher pedal thing, and either whatever you do, somehow you're applying that couple of M. Okay, so that one was easy. And the second one is that if you go to, if you want to specify what kind of thread to get on your square threaded screw, you don't specify it with that angle. So the thread angle isn't given in degrees. It's given via either a pitch or a lead. Well, what's important to us is the lead, and here's what the lead means. If you have, so let me draw sort of an exaggerated, blown up view. So let's say you have a little ant or something that starts walking up this thread. Okay. And he walks this way around the thread. The question is, when he gets back to the same point on the screw, how much higher has he gotten? So he'd come around the back, come up this way, and the lead is this. That's lowercase l lead. Okay. The difference between that and the pitch, on this screw, the lead and the pitch are the same thing. But some square threaded screws are set up with separate tracks. They're called double threaded. And so if this ant like followed this path around, he would never touch this one. He would show up on a thread that was above this one. Okay. In that case, the pitch would still be this, but the lead would be where the ant comes out next. Okay. So now, if we still call R the same thing, so this is still that distance, little r. Imagine detaching that thread from the screw and pulling it out straight, okay? So straighten out one revolution of thread. And what you would get is a long thing like this. Okay, where this is the angle we want. The horizontal length is the circumference of the thread, so that's just 2 pi r. And the height is the lead. And so that angle then is just equal to the inverse tangent of L over 2 pi r. Any questions about that? Because that radius is a horizontal distance. It's not a, that's not an angled distance along the thread. And that's just a radius you can measure with calipers, so that's a really convenient thing, Well, when I go to the hardware store, I see it as pitch. It's probably different manufacturer to manufacturer. I don't know that. But if it's given to you as a pitch instead of a lead, you just have to know whether it's a single threaded screw or a double threaded screw. If it's double, you just have to multiply the pitch by 2. I will, in this class, in a non-real world, I will give you the lead. Oh, one more thing. Let's go back to that example and just figure out what the cup. No, I didn't give you a radius. Forget that. Any other questions? This one? Okay. It's basically, it's just the distance from the center of the screw to the outside of the thread. This picture that we're looking at right now, that is the screw, and instead of having a thread wrapping around it, it just has a block coming out of it that represents the entire thread. And the idea is that instead of calculating the whole thread sliding along the path, we're just calculating that one block sliding along the path because the area of contact doesn't matter.